Hello, welcome back to AC Circuit Analysis. This is the topic of delta Y problems. This is part 2. It's our second delta Y problem. So here's what we do here. We have a problem here, as most of them are. They're just text-based problems, and then what you have to do is you take the information out of that problem, you draw a picture. That's the number one thing you have to do. Write down everything that you can in terms of a picture, and then formulate a plan to figure out how to go step by step to finding the answer. So what we have is we have a positive sequence. That means it's a positive phase sequence. Balanced delta source. So this is kind of my shorthand way of writing that here. A positive phase sequence, balanced three-phase delta source, has an internal impedance, and here's what it is. It's 0.09 plus J, 0.81 ohms per phase in a delta configuration. It says this source feeds a balanced load through a balanced line. Not a big surprise. We're doing balanced three-phase circuits, so the line and the load would all be balanced. But the rest of the problem doesn't have anything to do with whatever is connected on the line and the load. It's all about what's going on in the source. So we say here, the next part, the B phase of this source has a line current. Well, I guess we do talk a little bit about the line. The line current I, little b, big B. Here's what the line current is, but we're given the line current for the B phase, not for the A phase, so that's a little bit weird off the bat. And then we're told that the line voltage at the source is V little a, little b, VAB is equal to, and here's what it is, 480 volts at an angle of 60 degrees RMS. And here's the punchline, find the internal source voltage VAB prime. That's what this little mark here is, right here. That's a prime, VAB prime. Now I mentioned this when we first talked about delta sources kind of at the end of one of those lessons. You might want to go back if you don't remember that at all when I talked about delta sources and introducing them all. I said, hey, if you ever see a problem where they're asking for the internal voltage source of the delta in the delta configuration, and they talk about a prime here anywhere, then what that's referring to is the actual voltage of the internal source. So remember, you have a triangle configuration for a delta source, and each leg of that triangle has the actual voltage mechanism, and each leg of that triangle also has an impedance. In fact, the impedance is given to us here, right here, for each leg of that triangle. So when they ask you what the internal voltage source is, what they're asking, which is what we're asking, find the internal source voltage, and they give you what the label is, AB prime. Mentally what you need to think about is when you zoom into that triangle, each leg has an impedance, a source impedance, and a voltage source. We want to know what the value of that voltage source is internal to that leg. Because remember, if I zoom out and treat the source as a whole thing, I have each phase of the source. I can measure the voltage drop across each leg of that triangle, and that would be, that'd be the voltage source on each phase. But since there's an internal impedance there, that's not the actual internal voltage source there, because remember, there's current flowing around that triangle. And so there's a little voltage drop for every one of those source impedances. So you have a voltage source, that's actually what's generating the voltage, and you have a little bit of a loss because of the internal voltage windings or whatever of the source is how we model it there. So what we want to do is zoom in to the actual source voltage itself, the granddaddy voltage source inside of the leg of the triangle, and we denote that AB prime, and we're going to draw a picture in a second to show you what that means. So big picture, we have a balanced delta source. We know the impedance of each leg on the delta source. We're given the B phase line current coming out of the source, and we're given the line voltage. That means line to line, VAB, right? And that's given here. But we want to know what internal to that A phase there on the source, what is the internal voltage source inside of the triangle. So the best way to do it, as I said many, many times, is to draw a picture. So you know you're going to have a triangle, so let's go ahead and kind of draw a little node up here. And we know that every leg of this triangle is going to have a resistive component, because you see the impedance here is a resistive component and an inductive component. So we'll draw a little inductive component here. And then every leg of this triangle is going to have what we call the internal voltage source, right? And we'll draw some polarity markings here. And so that's one leg of the triangle. Then we go over here, and then we have some other inductive part, some other resistive part, and then we have the second part, or the next voltage source of the, like this, of the triangle. And then on this side, we have this voltage source at the top, plus, minus. Here's the resistive part, here's the inductive part, and it goes down and connects to that triangle. Now, if this drawing here confuses you, like if you're like, how do I know which one's plus or minus? I mean, you can kind of look at it, whoops, what do I have down here? That's plus. So this is minus plus, go this way, minus plus, go this way, minus plus. You can see they're kind of all kind of circulating around like this. But if you forget this, or if you don't know where everything goes, what you need to do is go back to my lesson on three-phase voltage sources, delta sources, because first what we did is we talked about the delta source without any of these impedances in place, and then we added the impedances and we kind of drew this as a reference. So you might need to sketch that on your paper, or if you're allowed to bring a sheet of paper into an exam, you might want to have these sources sketched, because it's very helpful to quickly be able to write this down instead of thinking about it for 10 minutes, you know, kind of thing. So in any case, we have a few things to label here. We know that each one of these guys has an impedance 0.09. That's ohms, and a J 0.81 ohms. I'm going to label them all, 0.09 ohms, and then J 0.81 ohms, 0.09 ohms, J 0.81 ohms. So there we go, we have every leg of this guy here. And then we want to also label the terminals here. So we have little a, remember sources always have the little a terminals. And this guy over here is going to be little b, the b terminal, and this guy over here is going to be little c, the c terminal. Now, I want to draw your attention, I mean, I'm doing this over and over again to kind of drill it into your head, but when we were doing delta loads on the other side of the line, the load, the way we drew the triangle was we had load, 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 and we had A, B, C. But here, for the source, we have it labeled A, C, B. Everything is mirror image reversed. Because of the way the circuits are connected together, it's easier when you're drawing the schematics to have it mirror image reverse on your terminals here so that everything connects nicely. And I talked to you about that before when we talked about the delta sources. I just want to show you how I'm doing it. You could certainly do the problem if you labeled them backwards. It's just I want to show you that this isn't a typo and that this is why in your book it's ACB, but the loads are ABC. We talked about that before. It's because when we draw these connections out, they're more easily connected to the load there. So let's go ahead and do that next. We have obviously a line coming out from this terminal, and we have a line coming out from this terminal. And look, I put my C in exactly the wrong place, so I'm going to move that. So this is the C terminal here. And this guy comes down and goes here. So we have a three-phase source. We have three lines coming out. This is the transmission line. And off on the other side, we have either a delta load or a Y load. But we don't even care about it because the problem doesn't talk about our loads here. Now here's the punchline that one of the main reasons I want to draw these kinds of things. Obviously it helps to orient yourself. But if this is VAB, right? See, remember, if there were no impedances anywhere, like if this were, you know, we always talk about the ideal voltage source. The ideal voltage source doesn't have any internal impedance, right? Real life voltage sources like this does have an internal impedance because everything you build in real life has windings and so has impedance and resistance and inductance, which is what we have modeled here. Now in real life, it's not a voltage source in series with these things. In real life, this source impedance is inside of this thing because the voltage source has the impedance in there. But schematically, we draw it as a perfect voltage source in series with some impedance. That's what we call the source impedance, right? But the point is if we were looking at an ideal voltage source, we wouldn't have this impedance, and we wouldn't have this impedance, and we wouldn't have this impedance. If it's an ideal delta source, it would be a source in this leg, a source in this leg, and a source in this leg, and that would be all there would be. So in an ideal voltage source, if I measured VAB, the voltage from here, this line to this line, it would just be the voltage across the voltage source. So if this were an ideal voltage source, if there were no impedances anywhere, then to find out what the voltage source in this leg is for the A phase, we would just measure VAB. That would be this value here, right? But notice in this problem, VAB stretches across the whole enchilada. So clearly, if this is the voltage here, there must be some current flowing through this leg. And so there's going to be some small voltage drop through this impedance here. So that means that this actual internal voltage source is going to be different than VAB. It has to be different because if VAB is across the whole thing and there's a voltage drop here, then this has to be different. So I guess what I'm trying to say is when you have real voltage sources and they ask you in the problem statement, find the internal source voltage and they give you VA prime, what you really want to do is you want to put another marking on your drawing. You want to put another kind of reference for yourself right on the other side of the source. We call that B prime. Why do we do that? Because the voltage drop between A and this point here is what we call VAB prime. That's actually what we're trying to solve for, the voltage drop just across the source. So we invent a new, I mean, you can put dots anywhere and label them whatever you want to help you solve your problem, but we're putting a dot right on the other side of the source. We're calling it B prime. We call it B prime so that we know it's different than this B down here, which is on the other side of the impedance here. None of this stuff is required, the B prime or any of that's, none of that's required if it's an ideal delta source, because there's no impedance for the source in the ideal delta source, so they're gone. Whoops, I screwed up my picture. And so we don't have any need for it. So the point is, if you're dealing with real sources and they're asking you for the internal source impedance, then you need to put a B prime. So you have VA B prime. And then you can do the other thing. Right here, you have a C. Well, I can put a dot right on the other side of the source, and I'll call that C prime. And here you have, let's see here, A, and I'll put a dot right over here. I'll call this A prime. So in this particular problem, we're asking what is the voltage for the internal voltage source VAB prime. That's the A phase, that's this voltage source. But I could also ask myself, what is the voltage source here? So I would call that BC prime. Or I could ask, what is the internal voltage source in this leg? That would be CA prime. You see how it goes? So you can measure the whole voltage drop across the leg, which includes the voltage drop across the internal source impedance, right? But if you don't want that, if you just want the actual pure voltage, as we model here, the pure voltage source of the generator, it has to be just across the generator, not including any of this impedance, so we have to put this other marking here. The reason I'm harping on it so much is because very, very rarely would you be given a circuit, a three-phase circuit, like a drawing to do it. I mean, if I gave you the drawing, it would be just too easy for you to figure it out. So most of these problems just give you a lot of words, and then you have to know what AB prime means. And so I'm trying to teach you kind of what that is at the same time as showing you how to solve the problem. So bottom line, you have primes in your nomenclature. You're going to have to put some dots on the other side of your sources. All right. In this case, we want this one. So let's go ahead and continue labeling some important things. What else do we know in this problem statement? The B phase line current, BB, is this, 6 at an angle negative 120. So I'm going to do that in a different color. That means that this guy right here, this current going like this, is I little b big B, and it's 6 at an angle negative 120 degrees, amps of course, right? That's the current, we always say the line current coming out of the source, and this is the B line current, okay? And then the other thing that we know is the line voltage VAB. That means VA measured to the B line. It's line-to-line voltage source. So the way I'm going to do this is I'm going to put a plus sign here. I'm going to put a minus sign here, even though this is in the way. I'm sorry about that. But measuring from here all the way to here is what we call VAB, and that's equal to 480 at an angle 60 degrees. So you want to label everything, even though I know my labeling wasn't perfect, but you get the point. You have a line current coming out here, and you have a voltage drop measured across this. But we don't want to find this voltage. We already given this voltage drop. We want to know what this one is. So then you have to ask yourself, now that you have the drawing, how do I find this voltage source, VAB prime, given everything that I have in the problem statement? How do I do that? How do I inch from what I have step by step to get to the answer? Kind of try to come up with some kind of formalism in your mind before we waste our time doing something. So here's the strategy. What we want to do, what we're given, is we're given this line current. So here's a line current coming out of a delta source. So remember, how do we, and it's a line current for the B phase, okay? So how do we convert? Remember, there's a difference here because we have a source, a delta source, so we have phase currents going around these triangles across each phase. And then we have line currents. Obviously, the line current for a delta source is different than the phase current in any one of these legs because of these nodes here. So the current coming out in the line has to be different than the ones in there. And because they're different, we have a conversion rule that we've been using this whole course. So we know how to convert between line current and phase current for delta sources, just like we were doing for delta loads. So if we apply that square root of 3 rule, we will be able to convert this B phase line current to the associated or its partner pair phase current. So we would convert from this line current to the B phase current. What would that be? That's going to be this guy here, because it's, remember, it's AB, BC, and CA. So the partner pair of the B line current is going to be the current going between B and C in this leg of the triangle, BC, right here, okay? So we could take this and easily use a square root of 3 rule to get the current here in this leg of the triangle, right? Now, we know that it's a balanced three-phase circuit. We also know that it's a positive phase sequence. Once we have this leg of the triangle, since each of these currents circulating in this triangle, they're a three-phase set. Once I know this one, I can either add or subtract 120 degrees to get either one of the other two. So once I know this one, I can add or subtract 120. We'll do the math later and we'll figure out whether it should be adding or subtracting later, but in principle, once you have this one, you add or subtract 120 to get this current. Once you know what this current is in the triangle, then you can solve for this. Why? Because you know the voltage drop across the whole thing, you know the current flowing through it, so you know the voltage drop across this impedance, and then you just do Kirchhoff voltage law, right? Because it's a voltage loop. You have a voltage drop here, a voltage drop across this impedance, and then of course you're solving for this voltage drop, and you just do the math. So that's the strategy. Map using the square root of 3 rule from this to get to this current, and then do add or subtract 120 to get to this current, and then Kirchhoff voltage loop to get this voltage. And that's what you want to do. You are going to have a very hard time figuring that out in your mind if you don't draw a picture. I mean, it really would be difficult. So I couldn't have done it. So I strongly suggest draw a picture, even if you don't think it's going to be helpful. All right, so the first thing we're going to do is we're going to convert that. Now, when we're dealing with delta sources and line currents and all this kinds of stuff, when the currents are different, we have a conversion rule, and that conversion rule is going to be the line current is going to be equal to the square root of 3 times the phase current, whatever phase you're talking about, the partner pair of its line current with its phase current, and then you're going to have to shift by either plus or minus 30 degrees. So how does that work in this particular case? For the B phase, it's going to be IBB is equal to square root of 3, okay? What's the B phase here? Well, this is the A phase going from between A and B. The B phase is going here. Now, here's something, another aside I need to tell you about. I hate doing this, but if you think back to delta loads, you have A, B, and C nodes of that triangle, delta loads, right? So the current circulating around in that triangle, we called them AB, BC, and CA. AB, BC, CA, just goes like the alphabet over on the load side. But because everything is mirror image reversed, and because, more importantly, the currents, we don't typically label, like for instance right here, we know the current must actually be going this way in this phase of the triangle because this is the voltage source, so it's supplying current. So it has to go this way. So because we've labeled their triangle, we could label it AB, but typically we write AB to denote current flow the other way. So because these are sources, we actually label this current IBA. I'm going to go ahead and label that for you right here. So this guy is typically going to be labeled IBA instead of AB. You flip them backwards. And between here and here, in the load, we would say it was IBC, but really because the current's going the other way, we label it CB. And then here, instead of C going back up to A, we actually label this guy going AC. So when you're dealing with delta sources, the currents circulating in each leg of the triangle have subscripts that are completely backwards of what you would have done over on the load side. And that just leads to another level of confusion. To be honest with you, it's just a label. It doesn't really matter what you call it. I just want to point it out to you because I'm a human being also. And so I might actually write down, for instance, I was about to write down BC here. I was going to write down IBC right here. Where's my pencil here? I was going to say, this is the line current. The phase current is BC. I was going to write IBC, and then the phase shift here is going to be either negative or positive 30 degrees, right? But then I remembered, oh man, for sources, we don't write IBC because everything's flipped around. You see, IBC would indicate that line current is going, or that phase current is going this way. But since we know it's a source, the current has to be coming out here. So for all sources, everything's flipped around, so really it's ICB. The reason I'm bringing it up to you is because it's very easy for you to accidentally write it backwards. I don't think you'd really be counted off on the test if you wrote it down backwards, but I just want to let you know that I'm human also, so I might accidentally write it down. So just in your mind, if you see it for a source, and I'm talking about the phase currents, if I write down AB, actually it's going the other way, BA. And that is important for you to know, but just kind of keep in mind as we go through the calculations. So the line current is the square root of 3 times the phase current with a phase shift, and since this is a positive phase sequence problem, we just choose the positive sign. Then we go back to our problem statement and we say the line current, BB, is equal to 6 at an angle of negative 120. So we say 6 at an angle of negative 120 is square root of 3 ICB, angle negative 30. So if we're going to solve for ICB, which is the phase current going through the bottom leg of that triangle, it's going to be 6 at an angle negative 120 divided by, well, you know what, let's save a little bit of room. It's going to be this guy here, it's going to be 1 over square root of 3. 1 over square root of 3 because we move this over. Then we have what we're multiplying here. And then we take and divide by this phase. But when we do that and we bring it back upstairs, it's basically plus 30. We've been doing this enough now where I don't need to keep writing it over and over again. We're solving for this. So we divide by square root of 3. But when we divide by the negative 30 phase, it actually becomes a positive 30 phase on the other side. So then we can do the actual math and say ICB, the phase current down there. Let me just double check that I've done everything correct so far. Is going to be 3.46 at an angle of negative 90 degrees. And that's amps RMS, of course. All right, so this is not something I'm going to circle. I'm just going to put an asterisk because it's important. ICB. We have taken the line current and we found its corresponding partner phase current going from C to B. So we found this guy right here. I could draw it. Yeah, I could go ahead and put it there if you want. ICB. That's what we found. That's the phase current. Next thing we want to do is figure out, now that we know the phase current, how do we find this phase current? We know it's a 3-phase set, so instead of getting yourself confused, go over here and draw yourself a little picture, which I always do. And so we're going to draw a phase sequence diagram. So we have some A phase. Now, again, I know that the subscripts are reversed, but it's just too much hard-coded in my head that this is the A phase. It's called AB. For a positive phase sequence, this is going to be the B phase. So this is BC. And this is going to be CA, okay? Now I know that because this is the delta source, this is really called IBA, and this is really called ICB, and this is really called IAC. I know that. But really, I just don't want to rewrite it again because it's such habit here. So this is going to be negative 120 to get from A to the B phase. And this is going to be adding 120 degrees to get from the A phase to the C phase. That's what you want to know, basically. Now, what do we have here? We're given CB, which is what I told you. This is flipped around. I mean, if you really want, I can erase all these and flip them all around. But basically, this guy is this one. So how do we go and get the A phase current, which is this one? How do we get this one? Well, we start with the B phase current, which is what we just calculated. And we add 120. Add going against this guy. So we add 120 degrees. So that means that IAB, but we flip everything around in the subscripts, BA, is going to be equal to this phase current we just found, 3.46 at an angle negative 90, but then we have to add the 120 degrees. Whoops. Add 120 degrees. Like this. So IBA is 3.46 at an angle. When you add these together, you get 30 degrees, positive 30 degrees, amps. BA. This is IBA. This is this current flowing from the B terminal to the A terminal is 3.46 at an angle of 30 degrees. Double check myself here. All right, so now we're actually getting very, very close to the answer. Because now we know, because of the problem statement, we know what the voltage between A and B is. It's given by this, right? As if this is a positive terminal and this is a reference. We know the current is going in this direction, so there's some voltage drop here. This will be a plus and this will be a minus if it's going this way. The voltage drop is like this, and we want to find this. The easiest way to do this, so you don't get confused, is just to write a simple Kirchhoff voltage loop. So you start at this terminal and you go up to a voltage rise. This is a voltage rise, so we'll just call it voltage rises. Remember, are treated as negatives in KVL, so we call it VAB. Okay, it's a voltage rise. Then we come over here and we have a voltage drop. We treat that as a positive, so plus VAB prime, right? And then we go here. Notice what's going on here. We're going down through here. Now this would be plus minus, so this would be another voltage rise, a voltage rise. So we treat that as negative. And what is the value of this voltage? It's the current times the impedance. So we call it IBA times that impedance, 0.09 plus J, 0.81. That's everything. We've completed the loop, and that's equal to 0. It's actually crucial that you understand this equation, otherwise the rest of the problem doesn't make any sense. So you want to find what this unknown is, so you just create a KVL. You start here, you have a voltage rise, so you treat that as negative, right? Then you go here, you have a voltage drop, you treat that as positive. Then you have another voltage rise, because it's going against the grain of this current reference we have. And the value of this voltage rise is this times this, right? Ohm's law. And then you're back to where you started, so you have a complete KVL equal to 0. The reason I like to do it as a KVL is really what you're trying to find is, let's move it over here like this. We'll say VAB is equal to VAB prime minus, yeah, it's a little bit cumbersome. I just have it written down in my notes a little differently. I'm sorry about the inefficiency here. IBA. Sometimes I do these problems and then I'll look at my paper when I'm doing it in front of the camera here, and sometimes I realize, why did I do that? I could have just saved a step or whatever. But I'm trying to keep in sync with my notes so I don't screw something up. So what I did is I write the KVL on the first line. All I did in the second line is move this to the other side of the equal sign, making it positive. Everything else is exactly the same way as it's written there. So now we want to go ahead and plug in what we know. VAB is equal to this, 480 angle 60. So 480 angle 60. VAB prime minus IBA, we just found that, that's this guy, 3.46 angle 30, 3.46 angle 30. We're multiplying that times this impedance, 0.09 J81, like this. All right, now here's where we're going to kind of do the magic of calculation here. Grab your calculator. You take these two complex numbers, multiply them, and you add it, because you're doing the opposite, you add it to the other side of this complex number. And then what you get is that VAB prime is 481.68 at an angle 60.27 volts RMS, of course. 481.68, 60.27. What we found is we found the actual voltage phasor for this internal voltage source, and we figured out that it was 481, is the magnitude, 0.68, at some phase angle here. Now let's see if it makes sense. Just back of the envelope sanity check. What we're basically saying is this voltage source here is actually larger than the measured voltage on the outside. Because remember, this is a power supply. This could be inside of a box. You have 3 lines coming out. You have an A phase between 2 wires, and a B phase between 2 wires, and a C phase between 2 wires. What we have found out is that if we measure the A phase voltage, we got across the outside of the power supply, and we got 480 magnitude, right? What we're saying is that the internal voltage source is actually higher than that. It's 481 and some change. That makes sense, right? The internal voltage source has to be bigger than whatever we measured outside. Why is that the case? Because we had some internal voltage source, and we have losses in the internal impedance here because of the current flowing, and because of the actual voltage source heating up because of its impedance inside of itself, the resistance and inductance. So it makes sense that this guy is slightly bigger than the external voltage that is measured because we have some losses here. So we start with 481.68 magnitude. We have some losses in the voltage, which is subtracted from that, so that the external voltage that we get is actually a little bit lower at 481.60. So a lot of talking for a pretty simple problem. I mean, well, everything is simple in life or in math. Whenever you know how to do it, everything is, right? Even really advanced things. But the basic idea is you have to take this picture, you take this information, you have to draw a picture. When you have internal impedances, you have to create new primed points so that you can measure the voltage or have some reference to measure the voltage internally there. And then the strategy was we took the line current, we mapped it and equated to figure out what this phase current was. Then we used the fact that it's a balanced 3-phase circuit to add or subtract 120 to get this phase of the phase current. And then once we had that, we just did a KVL to find the only unknown in this loop here, which is this guy. It's a good problem. It's a practical problem. But just like I said with everything else, it's not a hard problem once you understand how to do it. So follow me on to the next lesson. We'll kind of do something, another problem similar to this. We'll have a little twist, make it a little different, but it'll have a similar theme.